Hi, I'm Michael McCarthy,
Cameron Bickford.
And I'm Ryan Ferdos.
and today I'll be discussing with you Lab 4, Digital Image Correlation. To introduce you to this topic, the goal of the experiment is to determine if digital image correlation can accurately portray a multitude of reactions to material properties, and also familiarize students with the DIC software. And we will utilize the software to determine Poisson's ratio for a series of samples. And these samples will be copper, aluminum, and polymer, dark bone samples. And we hypothesize that digital image correlation can accurately determine material properties for these said reactions. To give you a bit of background, what is the DIC? DIC is an optical measurement technique used to analyze and help calculate deformations, strains, and displacements in materials and structures. Why would we use it? The benefit is to allow for no contact or destruction of materials or structures while identifying strains, deformations, or displacements. Poisson's ratio. It is a material property that describes how a material changes shape when subjected to an external force or deformation. To calculate this, it is a ratio of the lateral strain over the axial strain. And this ratio tells us the magnitude will determine how much material will change shape under loading. A positive ratio indicates a material contracted in the perpendicular direction, while a negative ratio indicates that the ratio expanded laterally.
So we have the methods that we use to actually make this lab happen. So we had to first acquire the 3 dog bone samples that we were talking about. You have to load them into the clamp draws. You have to make sure we measure the samples, and we have to preload them to make sure there's enough tension in them before we start. Then we have to position the camera correctly while also making sure that we have enough lighting. And then after that, you'll start GOM Snap 2018. You'll initialize the sensor. We want to make sure that the measuring sequence is at 20 hertz and it has 120 image count. After that, we'll start loading the sample. We want to make sure that you don't do it past 100. That'll be a little too much. And then we'll put it into GOM Correlate to determine the strains after that. And then some of the controlled variables we had for this lab. The dimensions of the samples were pretty much the same. We try to keep them as close as possible. We try to make sure the camera alignment and the focus was, all the same. All the camera settings, and then the frequency and image count were all the same. By controlling all of these variables, we basically ensure that the results are very accurate, and hopefully you'll see that they work. So this is some of the pictures that we got. It's for aluminum, and then we got the copper, and then the polymer.
For the results and analysis, we found that the aluminum sample had around a 1% axial strain and a 0.25% transverse strain, and this was the lowest strain out of all the samples. The copper had an approximately 2.5% axial strain and 0.75% in the transverse direction. This shows that copper is more ductile than aluminum, and the polymer sample had approximately 5% axial strain and around a 1% transfer strain. The polymer sample had the highest strain out of all the samples, and that's also in line with expectations. So from this data, we calculated the Poisson's ratio for each sample. So for aluminum, we have a calculated Poisson's ratio of 0.28, which is about 15% off from the textbook counterpart of 0.33. For copper, we have a calculated Poisson's ratio of 0.3, and the textbook value for it is 0.34, so there's a percentage error of 11.7%. And for the polymer, we calculated a Poisson's ratio of 0.2, and the textbook values for polymer or polyester specifically falls between 0.15 and 0.5. So when comparing it to the average of, the average Poisson's ratio of 0.3, we have a percentage error of 33%.
With our results producing a relevant accuracy, as Brian had discussed, we can conclude that digital image correlation was successful in producing accurate values for Poisson's ratios and strain within the dog bone samples.
And for the future work and recommendations, things we could do to improve this experiment, we could use different clamps, and because slippage is always could be a problem. So, you know, if we use different clamps, we could get better and more reliable data. You know, higher quality equipment such as higher quality cameras would always help to provide more accurate results if we could, you know, capture more frames per second. And making the loading process more replicative will allow for more uniform measurements across the sample.
And, you know, all of our references right there.
Yep, and that concludes our presentation. Thank you.
Thank you.